Welcome to this explainer. If you've ever looked at a chemistry textbook and felt completely overwhelmed by the sheer volume of formulas, you are definitely not alone. It looks like alphabet soup, but today we're going to reframe how we look at these reactions. We'll discover that chemical equations aren't actually just random letters and numbers you have to memorize, but rather a completely predictable, highly logical molecular choreography. It's a dance.
But before we even try to memorize anything at all, we really have to ask ourselves, what actually drives a chemical reaction to happen in the first place? Like, why did two seemingly inert, boring substances suddenly transform into something completely new, with dazzling lights, or heat, or a sudden color change? Well, it all comes down to a fundamental set of logical rules that matter follows just to reach a more stable state.
So here is our roadmap to understanding the logic behind these equations today. We'll start with the language of chemistry, move into combining and breaking apart, check out the logic of trading, look at the exchange of energy, and wrap up with redox, flowing electrons. Let's jump right into section 1, the language of chemistry, tracking reactants and products. Okay, so we use word and balanced chemical equations simply to track who is starting this dance, which we call the reactants, and who is finishing it, the products. A word equation expresses a chemical reaction in plain, everyday language rather than complex chemical formulas. And honestly, this is incredibly helpful. It lets us immediately identify the cast of characters involved and establishes the logical flow of matter from start to finish, completely skipping the heavy math for now.
Moving right along to section 2, combining and breaking apart, two sides of the same coin.
Seeing how matter actually builds into predictable behavior starts with assembly and disassembly. In a combination reaction, it's just a simple coming together. The underlying logic here is fusion. It's nature's way of finding a simpler, combined state. Two elements, or maybe an element and a compound, merge to give you one single product. Think of a magnesium ribbon burning in oxygen. It reacts with this dazzling, bright white flame to form a single powdery white ash of magnesium oxide. It is beautifully straightforward.
But hey, what goes up must come down, right? Decomposition is the exact opposite. This is where a single substance breaks apart into multiple pieces. Usually, this needs a little bit of heat to get going, but it represents the logical unraveling of a compound. A fantastic example from our sources is zinc carbonate breaking down under heat to form zinc oxide and carbon dioxide gas.
And putting these side by side brilliantly illustrates that we're not looking at isolated equations you have to blindly memorize. No way. They are literal mirror images of the exact same chemical logic. On one side, you've got the building up of matter into a single product, and on the flip side, you have the breaking down of a single substance into multiple products.
That brings us to section 3, the logic of trading, swapping partners.
Now, sometimes it's a simple single displacement, where one element essentially cuts in on the dance floor and displaces another, taking its place in the chemical structure. And this is entirely driven by reactivity. The stronger, more reactive element essentially plays the bully and kicks out a weaker one. For instance, when solid magnesium reacts with hydrochloric acid, the magnesium boldly takes over from the hydrogen, forming magnesium chloride and releasing hydrogen gas.
Now, with double displacement, there is this fascinating step-by-step logic where two compounds completely swap their parts simultaneously in an aqueous solution. First, you have ionic compounds dissolved in water, which just means they're separated into freely moving ions. Next, these ions bump into each other and exchange parts, and finally, this often results in the formation of an insoluble salt, which we call a precipitate. To really visualize this, I want you to imagine mixing two perfectly clear solutions together, potassium iodide and lead nitrate. The very second they mix, the ions trade places, and suddenly, boom, a solid, dazzling yellow precipitate of lead iodide appears literally out of nowhere. I mean, it looks like magic, but it is pure, predictable, logical exchange. All right, on to section 4, the exchange of energy. Where does the heat go? So logic dictates that energy must go somewhere to balance the books of the universe. It either bursts outwards as heat in an exothermic reaction or gets absorbed endothermically. In an exothermic reaction, like when you mix quicklime and water, a massive amount of heat is giving out along with the product. Conversely, endothermic reactions act like these energetic sponges. They actually absorb energy from their surroundings just to keep the chemical dance moving forward. And finally, section 5, redox, flowing electrons, the ultimate power dynamic.
Historically, scientists kind of thought this was all just about gaining or losing oxygen, which, to be fair, makes total sense given how abundant oxygen is in our atmosphere. They called the gain of oxygen oxidation and the loss of it reduction. But actually, as we shift our focus to the modern electronic idea, the true underlying logic is revealed. It's actually all about the flow of invisible electrons. If there's one fundamental rule I want you to remember from the scientific texts we're looking at today, it's this. Oxidation is losing electrons, and reduction is gaining them. And because electrons don't just magically vanish into thin air, these two processes absolutely must happen simultaneously. If one species loses electrons, another species is right there waiting to gain them. This is absolutely crucial. It's the ultimate takeaway rule of this whole explainer. Think of this whole agent dynamic almost like a financial transaction. To get rich, or in this case, reduced, you need a donor, which is the reducing agent. To give money away or oxidize, you need an acceptor, which is the oxidizing agent. The substance that reduces itself by accepting electrons is acting as the oxidizing agent for the other. Meanwhile, the reducing agent donates its electrons, freely oxidizing itself just to help the other species reduce. It is a perfectly logical, beautifully balanced trade of chemical power. So, by framing these equations not as random strings of letters to memorize, but as logical patterns of assembly, displacement, energy transfer, and electron flow, the entire world of chemistry just opens up. So the next time you see a car rusting, a fire burning, or even just think about how you digest your food, ask yourself, which logical molecular dance is taking place right in front of you? Thank you so much for exploring the logic of chemical reactions with me today. Keep asking questions and stay curious.